So now we have spent some time not only learning about the characteristics of these graphs, but also figuring out how to find various things, finding zeros by factoring. We spent some time learning how to do polynomial division and including doing synthetic division to pick that process up a little bit. Now we're going to put those concepts together so that we can, now that we have those extra tools, to be able to extend what we can do with these polynomials. So this is getting into section 4.4 of your book. And what we're getting into now is finding real zeros of a polynomial. Now, there's two new rules that we're going to get into. One rule is that just a kind of a rule of thumb about polynomials, and that is that a polynomial cannot have more zeros than its degree. So what that does is that gives us kind of an upper limit of how many zeros we can expect to find. So if we have a fifth degree, or as I sometimes tend to say, fifth order polynomial, that has an absolute max of 5 zeros. We're never going to have any more than that. We can have 4, we can have 3, we can have 2, we can have 1, we can have none real zeros. We can't have 6, 7, 8, and so on and so forth. By the way, as a reminder, fifth degree also has a max of 4 turns or turning points. Okay, so a fifth degree polynomial that would be completely maxed out on its number of zeros and of turning points might look something like this. Here's 1 0, here's another 0, there's another 0, there's another 0, there's another 0. So you've got 1, 2, 3, 4, 5 zeros, and 1, 2, 3, 4 turning points. So that would be a fifth order that would be completely maxed out. So that's one of our rules. The next rule actually has a name. The name of this is called the rational zero theorem. Okay? The rational zero theorem goes like this. Let's say we have a polynomial of nth degree. So, for example, if we were talking about a fifth degree polynomial, then n would be 5. If we were to write this out in general form with our powers going downhill, our leading term would be first. So I'll call it p of x. And what I'll do is I'll first write the leading term. That's going to be some coefficient a sub n times x to the n power. And then you don't have to, but you could have a whole bunch of other terms. And then at the end, you're going to have a sub 0 for your term where x is to the 0 power. So we have our constant term at the end, a sub 0, right here. Constant term. And we have our leading coefficient right here. And those are the numbers that we're looking at. Everything else we are setting aside for a little while. Now here's what the rational zero theorem says. If we have a 0 of this polynomial and it's a rational number, here's how it's going to have to be. A rational 0 of that particular polynomial has to be a factor of the constant term divided by a factor of the leading coefficient. So it's best to explain this in the context of an example. So I'm going to go ahead and pop one up. I'm going to leave this up at the top of the screen. And I'll just pick a polynomial. F of x is equal to 4x cubed minus 3x squared plus 5x minus 6. Okay. Our constant term is that negative 6 back there. So let's see what the factors are of that. Factors of the constant term are going to be 1, 2, 3, or 6. Now, because that's a negative 6, we could have negative 1 times 6 would give us negative 6, or we could have positive 1 times negative 6. Likewise, we could have negative 2 times positive 3, or 2 times negative 3. So all of these numbers could be positive or negative. So what we wind up with is a total of 8 different options. Likewise, if we do the factors of our leading coefficient, we have our 4 as our leading coefficient. We could have plus or minus 1. We could have plus or minus 2 and plus or minus 4. Notice how I didn't repeat that 2. We don't have to, because 4 is 2 times 2, we can just list the 2 once. We don't have to repeat it. Well, what this means is that we have a list of possible rational zeros. Rat for rational, zeros. And they are, x could be, and rather than listing a whole bunch of plus or minus next to each number, I'm just going to put a plus or minus out in front because either the negatives are going to cancel out or they're not. Plus or minus 1, 2, 3, 6 up top, and 1, 2, and 4 down at the bottom. So we have to go through these and set up a list of possible rational zeros. And what we're going to see is that this list is going to collapse really fast, but it's going to start out a little pretty long. So let's start with everything that is over the 1 right here. Everything that's over that 1. 1 over 1, 2 over 1, 3 over 1, or 6 over 1. All right, next up, we'll try everything over the 2. That's going to be 1 over 2, 2 over 2, 3 over 2, 6 over 2. And lastly, over the 4, I think we're getting into a groove here. I'm running out of space, so I'm going to have to crunch it in there. 1 over 4, 2 over 4, 3 over 4, and 6 over 4. All right. Now, we don't want to have to do the same thing twice. There's no need to reinvent the wheel. So what we can do is we can cross some of these out because they're duplicate numbers. For example, 1 over 1, the first number in our list right here. That's just 1. 2 over 1 is 2. 3 over 1 is 3. 6 over 1 is 6. Now for over 2. 1/2, that hasn't been said yet, so we'll do 1/2. However, 2 over 2, we've already done that. That's the same thing as 1 over 1. It's equal to 1, so we don't even need to worry about that. I'll just skip that. Next up in the list is 3/2. Then 6 over 2. that's equal to 3. We've already got 3. So I'll skip that. 1 over 4, we don't have that part of our list. 2 over 4, that's the same thing as 1/2, and we already have that. So I'll skip that. 3 over 4, we don't have. 6 over 4, that's the same thing as 3 over 2, so we already have that. After doing this a couple of times, what you'll be able to do is you'll be able to go from this step to this step in one fell swoop. But for right now, it's just laying it all out there. Okay, now we have this possible list of zeros. Now, here's how we're going to narrow this down. I'm going to pause here for a second, explain what we're going for. Your book has a method for finding all these zeros, or at least approximating them, without a calculator to do anything more than just arithmetic. Here's the rub. Some of those techniques are extremely tedious, and they're mainly of interest only to theoretical mathematicians. And so, you know, one out of several hundred of my students might go into a field where they're doing that, and I think at that point, if they're interested in that, they can pursue it at that time. For the rest of my students, what I'm going to do is I'm going to do a much more pragmatic way of doing it, and that is that we're going to use our calculator. Our calculator has this very, very valuable graphing function. Didn't have this back in the day. That's why we have these non-calculator techniques. But we do have the calculators now, so let's use it. Graph it up. Need to go up here so I can actually remind myself of what I'm graphing. And we'll plug it in. 4x cubed minus 3x squared plus 5x minus 6. Graph. And there we are. So we have this graph now, and it looks like right here we are crossing the x-axis at x is equal to 1. Now we can't tell that exactly. This is our rational zeros theorem that gave us that 1 is an option, but that may be an irrational number that's really close to 1. So what we can do is we can test it out to see if it actually is 0 there. We'll plug 0 in. The fastest way to do this on your calculator is go second, trace, get to your calculate menu, calculate the value at x is equal to 1, press enter, and lo and behold, when x is equal to 1, y is equal to 0. So x is equal to 1 actually is a 0 of that function. So we graph it. X is equal to 1 appears to be that 0 there. F of 1 is equal to 0. We check that, and lo and behold, it is. So that tells us that we have just found a 0 there, and we're able to confirm by using the rational zeros theorem. Okay, so now we have shown that that is a 0, and we've been able to confirm it using our rational zeros theorem. So now we have a question. That raises a question. This is rational zeros. What about irrational zeros? Whatever shall we do? Well, the answer to that is, don't worry about it. For our purposes, if your 0 is at square root of 2 or something like that, odds are you'll come across it when you're factoring it out. But if you're not doing it by that method, if you're truly using just a regular calculator, not a graphing calculator, to find an irrational 0, it involves an iterative process called the bisection method. When it's an iterative process, what that means is you wind up going through the exact same thing over and over and over again and getting closer and closer and closer to your 0. This has kind of fallen out of favor since we now have computers that can do that for us. So therefore, we're not going to get into it in this class. Again, if you wind up being a theoretical mathematician in the future, I'm sure the technique will be a cakewalk for you at that point, but for our purposes right now, we're not even going to get into that. So what I have is kind of a more concise version of what your book presents as the way to find zeros. So here we go. Steps to find zeros. Okay, first of all, if you have a polynomial, it's all simplified out. You know what, I'm going to amend that here. Steps to find zeros if you can't immediately factor. If this is a polynomial that you can factor pretty readily, you don't have to worry about all these steps because you're able to factor it and find the zeros right away. First thing you want to do is you want to use the rational zeros theorem. To find candidate points or possible zeros that you would be choosing from. So I'm just going to call that a list of candidates. Next up, you want to graph the function using your calculator and fit your possibilities, your possible candidates that look like they might fit. For example, when we graphed that earlier one, it looked like one might be a zero. Next, what you're going to do is you're going to test those values. If, for example, f of a is actually equal to 0, a would be your candidate point. And if it is, x minus a is a factor. Okay, great. Now, x minus a, that's a linear factor. So what you can do is you can use synthetic division to divide x minus a from your original function. And then finally, lather, rinse, repeat if you have to. Here's the little name I'm going to give this process. Since we are dividing in order to factor and figure out what we need, we'll call this little technique divide and conquer. My math students have been bugging me to put in one of my notably bad puns into one of these video lectures, so there we go. Let's buy myself some room here. There we are. So here's our function. Let's work through it and give it a shot. X to the 5th minus 2x to the 4th plus x cubed minus 2x squared minus 2x plus 4. Okay, now when we at first look at this, we want to sit down and cry. But then we remember that we just need to walk through our steps. Our first step is to use our rational zero theorem. So let's build up a list of possible zeros. Rational zero theorem. X could be plus or minus all the factors of the 4 first. As a reminder, the 4 is what we're looking at right here. X is plus or minus 1, 2, and 4 are our factors of 4. Divided by the factors of 1, which is the leading coefficient of this polynomial. The factors of 1 is a pretty short list, plus or minus 1. So the options that we have are plus or minus 1, 2, or 4. Next up, we're going to graph it. Pull up my TI. Y is equal to, all right, plug this in. X raised to the 5th minus 2x to the 4th plus x cubed minus 2x squared minus 2x plus 4. We graph. And we're waiting for it to think. And there we go. I can see 3 zeros there. Now, what it looks like is it looks like negative 1, 1, and 2. Notice how negative 1, 1, and 2 are all part of our candidates right here. So it looks like our zeros are going to be at x is equal to negative 1, x is equal to 1, and x is equal to 2. Easiest way to test this out is to plug those numbers back into our function to see if it actually equals 0 at that point. Easiest way to do that, since we're already using our calculator, is to use the evaluation utility there. So you go to your calculate menu, number 1 value, test out negative 1. When x is equal to negative 1, there it is, y is equal to 0. So that's a 0. Test out x is equal to 1. There we go, y is equal to 0. Finally, x is equal to 2, y is equal to 0. So all of our guesses turned out to be right. 3 out of 3 ain't bad. Check, check, check. So what this tells us is that we have 3 factors we need to look for. X plus 1 is going to be a factor. X minus 1 is going to be a factor. So is x minus 2. So now we're in for the longer part of this. What we need to do is we need to use synthetic division to find out what we're left with after we divide all these guys in. So what I'm going to do is I'm going to work my way down the list. I'm going to do x equals negative 1 first by dividing x plus 1. Next up, I'm going to do x is equal to 1 by dividing in x minus 1. Then I'm going to do x is equal to 2 by dividing in x minus 2. So we're actually doing 3 different synthetic division problems. And this is why synthetic division is so great, because it makes this happen fast. All right, synthetic division for x plus 1. I got a negative 1 here. My coefficients are 1, negative 2, 1, negative 2, negative 2, and 4. We should expect no remainder here. Carry down the 1. Negative 1 times 1 is negative 1. Add negative 2 and negative 1, we get negative 3. And from here on out, I'm going to stop voicing out my steps to save time. 3, get 4, negative 4, get negative 6, 6, we get positive 4, we get negative 4, we add those two, we get 0. So our remainder is 0. These are our coefficients of what's left. So now we know that f of x is equal to x plus 1 times what we're left with when we divide it out, which is x to the 4th minus 3x cubed plus 4x squared minus 6x plus 4, and boom. So now we've simplified our 5th order down to a 4th order. Well, lather, rinse, repeat. Next up, I'm going to do x minus 1. Divide in x minus 1 to what is remaining here. I'm trying to cut this down bit by bit by bit. I'm taking it out one byte at a time. So now with x minus 1, I'm going to have a positive 1 outside my synthetic division mark. My coefficients are gleaned from here, 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 and here are going to be 1, -3, 4, -6, and 4. Carry down the 1. 1 times 1 is 1, and I'm going to stop voicing out my steps to save a little bit of time. -2, 2, 2, you get -4, multiply, you get -4, and 0. Again, no remainder, which is what we would expect. So now we've got f of x is equal to x plus 1, that's the byte we already took out, x minus 1, that's the byte we just took out, and what's left is now a cubic. X cubed from this minus 2x squared from this plus 2x minus 4. All right, so we've taken a fifth order down to a third order multiplied times some linear factors. Last but not least, we're going to do x minus 2. X minus 2, use synthetic division again. 2. We're going to put our coefficient of what's left right here. 1 minus 2, 2, -4. Carry down the 1. Perform my synthetic division. And so now we are finally left with f of x is equal to x plus 1, our first byte, x minus 1, our second byte, x minus 2, our third byte, and finally we have 1x squared, 0x plus 2. X squared plus 2. X squared plus 2 is irreducible. That would give us an imaginary 0, which we're going to deal with in the future. So this is how we can use synthetic division to actually help us factor things. It's a big help, but synthetic division fortunately saves us some time over using long division. Here's your practice, guys. Your practice is going to be on page 379, number 11, number 21, and number 45. Your book's instructions tell you to go through all kinds of goodies with number 45. What I want you to do with number 45 is do what we just did with our previous example. Use your process to factor it out. Good luck. I'll see you in the next class, and enjoy dividing and conquering.